All right, so Tuesday, September 9. All right, we just knocked out these right here. Wanted to do more projectile puzzles with you guys. I think we did some of these the other day. So we'll knock out some more of these. You guys know this page is due on Friday. Help you guys out. I did want to show you guys the setup for Projectile Lab tomorrow. I want to take you guys outside the balcony. And then you guys know to look for kinematic motion plays on Friday. So linear motion and projectiles. So let's look at this projectile motion lab a little bit. So, yeah, I got some fun stuff going on. So you guys know tomorrow, I take you guys out to the balcony. Can you guys take the meter stick and measure the height of this balcony? Maybe walk up the staircase. Okay. And then can you measure how far out the bounce ball in? Here, I got a whole bag of these bounce balls right here. These. I'm down here. Where you not down state? Actually, the question you just asked. Actually, look at that. On the paper, it's but on this, very downstate. The physics terminology for us is called coefficient of restitution. So when we get to momentum, you'll be able to answer how bouncy is the ball. Okay, so this ball, you're going land somewhere out here. Now, if you know this height, this horizontal displacement in gravity field, do you think you could, in principle, determine how fast is this launcher launching the ball? Right? Yeah. Okay, so have to figure that. And I don't want you to use a stopwatch, but here, part of your calculation, I'll see if you guys can figure this out from scratch. Okay? So good challenge, but I'll give you a hint though, is that I want you to calculate the time of fall based on this cliff height. Okay. And that'll give you a more accurate time than trying to use the stopwatch. Okay. So what does this launcher look like? Okay. Looks like this right here. This right here. Now, do you guys know this little protractor here? Protractor? Okay. And it has this exactly level. You guys see, well, imagine gravity was pulling like down this way. Okay. With this paperclip hanging at, look at this, 0 degrees from the horizontal. So now this angle is relative to the horizontal, isn't it? So if this paperclip's hanging straight down, 0 degrees to the horizontal, I could change this. And then this would look like 30 degrees to the horizontal. You guys see that? Like that. Okay. Now, I guess if you want to make it really complicated, you could do this. I mean, the information would be there. But a really simple version of the lab is just to aim this straight horizontal. Okay. So can you guys aim this straight horizontal? Okay. Then, look, you see a diagram right here. Look, I got a ball, got a little spring right here. Okay. Now, guys, this is a little squishy bouncy ball. Here's this is really important if you don't want to burn much time tomorrow. If you put the squishy bouncy ball in first, and then you ramrod this with the ramrod, then guess what gets stuck inside the launcher? Squishy bouncy ball, and then it's really hard to get out, and well, that's no fun. So if you want to have fun actually launching the ball, what are you guys going to do? Put the ball in first or ramrod it first? Ramrod it first. Now listen. You guys hear that click? Hear that click? Okay. Now I can pull this, and you got here. Bam. Okay, so it's pretty loaded. Okay. So I want to ramrod it first. Are you guys going to ramrod it first? Yeah, and then put the ball in, right? Is that what you're gonna do? Right? But wait. What is this? Short range, medium range, long. Hold on. Wait. Let's look again. Oh, is that 2 clicks? Well, I wonder what is long range. 3 clicks. Ow. How'd it go?
Oh, there we go.
So, I wonder how fast that was. I wonder what was that last speed. Yeah, probably some speed. I think you guys are gonna figure that out tomorrow. You know what? Let me throw in a little bonus question for you guys because I was gonna throw this to my honor students today. So we'll do some bonus questions right here. Okay, we got a boy on a tower. Throws the ball. Now, does he throw it horizontally? Just like you guys are gonna do in your lab tomorrow? Let's say it lands 20 meters out. Actually, this is your lab question tomorrow, isn't it? Wow. Yeah. All right, well, why not? We'll do it here. Okay. So he knows the height of this tower. He knows how far the ball goes. What is his pitching speed? Get a good look at. No, guys, this book is a Paul Hewitt book. Paul Hewitt wrote it. So these are supposed to be stripped down simple enough. They're not supposed to be super complicated. Okay? Like there's a reason he made this tower 4.9 meters tall. Right? Or I might call that 5 meters tall. I'm rounding a little bit. All right, so go ahead and solve that. See who gets this first. Who's going to get this?
Like 10 meters or something.
Who knows the answer?
It's a 10.
Nah,
I didn't do that. No.
faster than that.
Well, yeah, if you has to get down. If that's 20 meters, in half a second. Oh, yeah, that makes sense. 40 meters.
So throw in it, you guys.
It's 40 meters per second, not 10.
Not that fast.
No.
Okay.
20?
Huh?
20?
20 what?
5.
What's the unit? Meters per second. Yeah, let's call it 20 meters per second. That's the answer. Right? So, guys, before you get the speed, first you have to solve for what question did they not ask? You have to solve for first. How much time? How much time? Okay? Because however fast it throws it, isn't it going that speed across the field the entire way? Or I should say the horizontal component velocity never changes, right? So if it went 20 meters in some number of seconds, it would just be like that many meters per second, wouldn't it? Okay. But how many seconds does it take? Ooh, because what if he dropped the ball at the same time? What if he throws the ball and he drops the ball? Do they take the same time to reach the ground? You guys remember that? Okay. So really, how much time does it take to fall about 5 meters? 1 second. You guys remember that? 1 second? You guys remember dropping off? Isn't it a simplified version of this right here? So if you drop the ball, be not 0. Okay. So G is about 9.8 or 10 meters per second squared. Right. So then in 1 second it will fall on 5 meters. Isn't that true? Right. Actually, 4.9 meters is if you use 9.8 meters per second squared for gravity. That's right. I chose 4.9. Okay. So 1 second. So it takes 1 second to reach the ground. Right. Oh wait, what if he throws it? Is this V naught still 0 if he throws it horizontally? Guys, this equation would be which rate does gravity pull? Down, vertical. Okay, guys, if you're pulling out this equation, working with projectiles, and you're using the whole thing, including this acceleration due to gravity, this is only a vertical equation. If he throws it really hard to the side, how fast is it leaving his hand vertically? 0. This is still 0. So it's still the same time. It still takes 1 second to reach the ground. Okay? And that's strictly a vertical question. It takes 1 second to reach the ground. Once you know 1 second, okay, it went 20 meters across in 1 second, must be 20 meters per second. Okay? Guess what? Another challenge question?
Sure.
Actually, this one's pretty hard.
We could do math for this one.
Maybe. The zookeeper devises a rubber band gun to shoot food to a monkey who's too shy to come down from the trees. So here he is with a slingshot. Oh, he's got a banana. Ooh. If the monkey does not move, so you're gonna get that banana to the monkey, pew! But let's say the monkey just hangs on to the tree branch. Should the zookeeper aim above, at, or below the monkey to get the banana to the monkey? Above. How many I say above? Above. Yeah, I think everybody says above, right? Because it's gonna be some kind of parabola. Now if he shoots it really fast, he shoots a little bit above, he goes, pew! Banana pudding. Or maybe if it just wants it kind of slow, it's like, maybe it's like, but it's some form of a parabola, right? Some form of a parabola. He does have to aim above. Okay. Unless you turn gravity off. What if you turn gravity off? Now he has to aim straight at the monkey. I guess not only in that case, right? But with gravity, it's always about the same. Right, now here's the tough question. Here's the tough one. Tricky one. Okay. If the monkey lets go of the branch at the instant the keeper shoots the banana. So they both release at the same time. Right. Then should the keeper aim at above, out, or below the monkey to get the banana to the monkey in midair? So part of the condition is that suppose the monkey's supposed to catch the banana before he hits the ground. Okay, before he hits the ground. Right. Okay. Give you guys a little time to think about that one.
Because the monkey's also moving, so it has to go a little bit. Well, example, it's that.
Something all great, yeah, great.
There's a hint right there.
I think it's for. Yeah, yeah.
Alright, let's see what you guys came up with. So here's your three options, above, out, or below. Show of hands. How many guys say he should still aim above the monkey? Who says that? Who says he should aim right at the monkey? Who says he should aim below the monkey? Ooh, I think I saw most hands on at. It was pretty close to 50-50 split between these two. Right? But yeah, he should aim at the monkey. At the monkey. Right? Here's why. Now this is a little tricky. Like intuitively, most people say, well, shouldn't he aim below the monkey? Because the monkey's falling, you should aim it, right? But guys, while the monkey's falling, is gravity also pulling on the banana at the same rate? At the same rate. So the monkey just falls some vertical displacement, just 1/2 GT squared, doesn't he? Just straight down. Straight down. Right. So I can say his vertical displacement would be well, y equals 1/2 GT squared. Right. Okay. Now, what about the banana being shot? Right. Now, if there was no gravity, then the banana would follow exactly the dashed line path. In fact, if there was no gravity, he should definitely aim at the monkey, right? Even if the monkey lets go of the branch, everyone just float around. So banana straight to him, right? Right. But because there is gravity, the banana is going to deviate from this dashed line path by well, I should maybe subtract off some gravel, shouldn't I? Right? Because the vertical position of that banana, if there was no gravity, it would just be like y equals v naught yt, right? And that would be the whole thing, right? But the fact there is gravity, you're going to deviate from that path by some amount, 1/2 GT squared, which is exactly the same amount that the monkey falls. So they both deviate from this position by 1/2 GT squared. Yeah, that's why you have to aim straight at the monkey. All right, that was fun. All right, let's do some. Some puzzles. Right. I think the other day I did this one and most of this one with you guys. I think. Right. Should be here. Right. I did these two with my honor students yesterday. Maybe we'll look at those. Okay, so let's do number 9 and 10 right here. Number 9 and 10. A cannon fires a cannonball horizontally at given speed off the edge of a cliff of given height on an alien planet. Ooh, alien planet. So cannonball lands some given horizontal displacement away from the base of the cliff. So what is the acceleration and gravity on this planet? And also, what's the total speed the cannonball hits the ground? Now, you guys know how I organize this table. As I give you horizontal information in this left side, I give you vertical information on this right side. Actually, I'm going to change it because you guys know I have lots of different versions. Let me find a completely new version. Have I used this one yet? Okay. All right, this one's brand new. Right, this one. So brand new. All right, so this is the horizontal information here. Here's vertical information right here. Okay, so I'm just going to take the scenario, draw the picture, and we'll see what next. All right, so this is number 9 and 10 on the projectiles. Number 9 and 10. Okay, so got a clip going. All right, we got a cannon aimed straight horizontally, just like your lab tomorrow. Be straight horizontally. Actually, all these 3 scenarios on the left side of the page is a cannon on a cliff aimed horizontally. The cannon is aimed horizontally. And what I give? Okay, so you draw this out. There's some blast velocity called speed sub x, and this cannonball lands somewhere there. My picture's probably not going to be to scale, but you're right. Work with that. Now, on my paper, here I got some other things. I got a height of a cliff. Well, I could call this H or Y. Actually, on the table I wrote Y, but Y could be H, right? Cliff height. What else we got? I told you X, how far away it lands. I told you that. this distance from here to here. Okay. And I did explicitly type v naught y as 0 because if you aim it horizontally, it doesn't have 0 initial vertical velocity. Right? Okay. But you guys know most physics textbooks or an AP question would not print the number 0 here, right? You'd have to figure that out. Right. Okay. All right. So throw some numbers in here. So my paper has this as exactly 100 meters per second. So that's my blast speed. I gave the height of the cliff right here as 17 meters. Now, of course, your numbers are probably different, but they're probably not crazy different. Okay. And then I've got mine landing 152 meters away. Okay. And there's enough information there where you can solve for the gravity code. Okay. You guys okay? Okay. Now, of course, you could solve in terms of variables, which is a good practice, or you could just plug in numbers from the get. Either way, it should get you the answer. Do you want to start with vertical information or horizontal information on this one? Huh. Okay. Let's see. Show of hands. How many guys say we should start with horizontal information? Horizontal. Who said that? Okay. Yeah, I agree with you because we know how fast the cannonball's going across. We know how far it ends up going. Therefore, we could very quickly solve for what?
Time.
Time. Yeah, how much time? Okay. So here's our game plan. Once we get time right here, guys, is it the same time to go across as it is to fall vertically? It's the same time. This time would be this time. Time is a scalar. Okay. So, and then we'll have 3 vertical type values, and okay, and then we can just solve the rest of it from there. Right? That's it. Right. So, here. Okay. So I'm going to start with horizontal information. Right? And if you're writing your notes, so if you're looking back in your notes, say if you're studying for the midterm or in December or whatever, but okay, that's right. Start with the horizontal. I can say x equals v sub x times t. Isn't that the only formula you need for projectiles in the horizontal direction? Yeah. Because there's no acceleration horizontally. It's always going to be x equals vt. Plug some values here. So I know it goes this many meters across at the speed across for some amount of time to crash land. Okay. Therefore, t equals, okay, should be like this many seconds. Okay. You guys got the time for yours also? Okay. All right, so everybody's got their time, right? Someone's got their fall time?
Yes.
And now that you know the time, would that be the same as what the cannonball just roll off the edge and straight down? Would it take the same time to hit the ground? Yes, it would. Right, same time, hit the ground, same time. Okay. And since you know the height of your cliff, you switch over to vertical and get gravity now. Okay. So go ahead, set up the vertical equation. So vertical. So the height, we can say y or h equals not y t 1/2 gt squared. Okay. And guys, what is v naught y again? Whether you drop the ball or you launch it horizontally, either way, v naught is 0. Yeah, 0. That's just the way. So h is just 1/2 gt squared. And okay, in this case, you know time, so I can plug that in. This many seconds. Okay. And okay, we're solving for g, and I know the height of the cliff. My cliff is this many meters. Okay. In fact, if you were being tricky about it, could you substitute t in terms of variables and say, well, t is x over v sub x, right? You could solve this whole thing in terms of variables, right? Yeah. But here, I made it this far. So I'm going to say g ends up being, can you guys finish off the algebra? Cross multiply the 2. So 2 times the cliff height divided by the time squared. Okay. Oh, and while we're at it, look at the units. You guys got meters over a second squared. Is that called meters per second squared? Hey, that could describe a gravity field. Oh, we're on the right track. Okay, so I'm getting this many meters per second squared. Let me make sure that's a answer choice on my paper. And hold on. Did I mess up somewhere?
Closer to 5.
2h over t. 2h over t squared.
14. Plus though.
What happened? Hold on. We gotta reset this thing. Every once in a while, this calculator freaks out. Because that doesn't look right. That doesn't even look right. Because 34 divided by something would be less than 34, wouldn't it? Right.
Yeah.
Here, memory clear. Memory clear. We're gonna try that again. 2 times 17 over 1.52 squared. Yeah, that's totally different. Okay. Yeah, like 1 in 10,000 times this calculator freaks out. Most of you guys do have a reset button on the back, so you just go pop that. There are a few calculators that do not have the reset button. Although you can do second zero. Maybe I should have tried that. You can do second zero to reset it that way. So this is 14.7 meters per second squared. Okay, 14.7 meters per second squared. Yeah, okay, and that is an amp, of course. Okay, so we're good. You guys good too? So now we know the gravity field. Right, you guys got your gravity field?
Yeah.
Right. Now back to the picture, because there was another question. What's the total crash speed? So as this cannonball is about to hit the ground, it's moving really fast. Well, how fast? Well, I think it's kind of coming. You guys see how, here, watch. I'm holding my ruler flush to the curve. Or maybe, yeah, I'll do it this way. You see the curve better. Flush to the curve. And right as it's about to hit the ground, it's kind of coming in on sort of this angle right here. I'll call it V crash. V crash, just like that. Okay. Now, that V crash kind of break that into components to say, well, it's kind of going across the field and it's kind of coming down at the same time. Across and down. Something like that. Right. And actually, I know,
I know.
what is Vx? What is that?
100.
Yeah, it was given. That never changed. Right there. And I kind of call this V final and the Y direction coming straight down. And that we haven't solved yet, but you could. Now, what do you guys feel like doing? Do you want to get the crash speed based on the fall time or the height of the cliff? What do you feel like?
Middle one.
Middle one? Okay, in terms of time. Okay. You guys know, of course, they would give you the same answer either way. So let's do middle one. Sure. So V final in the Y direction equals V initial in the Y direction. I'll say plus GT. Down is positive. This goes to 0. There. So V final in the Y direction is, I'm going to take my gravity field, which is 14.7 meters per second squared. Right. By the way, do it feel a little bit light or a little bit heavy on this planet?
Little
heavy. About 1.5 times my normal weight. Because on Earth, this should be like 9.8 or 10. Yeah, so a little bit heavy. And like noticeably so. Okay, and then for, what was the time? Okay, this many seconds. We got that.
Might even be
30 seconds. Guys, what is meters per second squared times seconds?
Meters per second.
Meters per second. Describes the velocity. Oh, yeah.
Oh, but of course.
Yeah.
Oh,
7 times 1.
I did not do that. Probably gonna have to make it take much more time.
Meters per second. And so that's how fast it's coming strictly down. Or strictly down. Okay, and you guys are following with your paper too? Your numbers?
Yeah.
So it's coming down at 22.4 meters per second. Okay. Now, if you know how fast to cross and how fast down, then how do you find the total crash speed? You apply the what?
Wow.
Pythagorean theorem.
Hippopotamus.
Pythagorean theorem. Yeah. So it should be burn it up. A squared plus B squared meters per second. I'll pull that up. The square root of 100 squared plus 324 squared. Okay. I'm getting 2.47. Yeah. There you go. You guys ever you guys know my picture is not to scale. You guys ever notice if you have a right triangle and it's this would actually be a pretty skinny triangle, wouldn't it? Like 100 compared to 22, like that's 5 times the width compared to the height. Okay. So the overall speed, like the hypotenuse, is just a little bit more than the long leg. Yeah. That should be the answer. 102 point something. Yeah, right there. 102 meters per second.
That's less than scale. Nobody would say that.
Alright, that work out for you guys? You guys help that?
way less. Dude.
All right. Now you guys know that these three scenarios on the right, you can basically use this picture. You guys see that? Okay. In fact, this set here, 11 through 14, number 14 says how far does the cannonball go horizontally? Okay. So you can do step by step by step by step by step. You know, kind of like we just did for the last one. You solve this variable, solve this one. Okay. But could you, for number 14, could you check your answer with this right here? Okay. Oh, by the way, here I'll take you guys through this a little bit. Okay. So this this range formula for a flat plane, this is for like pre-solved. So does it mean the blast speed squared divided by the gravity field times sine of the double angle? So if this angle is 30 degrees, you put in 2 times 30 would be 60 degrees. Is that right? Here's the entire derivation right here. So vertically, ooh, guys, if you go from the ground back to the ground, what's your vertical displacement? 0. So in place of y, I put 0 meters equals v naught y. There's v naught y. It's v naught sine theta, right? The velocity times sine theta. T minus 1/2 gt squared. Is that true? So here's the hang time. Okay, here's the hang time. You just solve for rearrangement. Okay. Now horizontally, x equals v sub x times t. Wouldn't that also be true? Right. But this t is actually that expression right there. Right. So then clean this up a little bit. Right. Now look at this right here. Does anybody know what this is? 2 sine theta cosine theta. Have you guys learned that in math class? Something called a double angle identity. Have you guys ever seen that?
Sorry, we have one.
Oh, someone had. Yeah, a couple of you guys have. Okay. So sine of 2 theta ends up being exactly right over there. Say a little substitution. This ends up telling you how far it goes. So you can check your answer with this. First of all, give you the right answer. Right. Right. Got about 3-4 minutes, something like that. 3 minutes. Okay. Guys, these 3 scenarios on the back are all the same scenario. I just changed the numbers a little bit. So they gave you a gravity field. Looks like on this paper they're all Earth gravity.
Sine could be cosine if you wanted to.
Got a cannon on a cliff. I told you the height of the cliff. And I told you this ramp angle. So many degrees. And I told you the blast speed of the cannon. So with all of that, can you ultimately figure out how far down range does the cannonball go? That's the ultimate question. Okay? Now the first scenario, I'm really helping you out because I'm breaking it down step by step by step. Like first find the components. How fast across and how fast up is that cannonball going? Isn't that these two right here? Right? Guys, why do I call the vertical initial velocity? Why am I giving you guys the negative sign here? Yeah, because if I'm calling gravity positive, which I did right here, then I have to find down as positive, which means you're kind of blasting it upish. So this better be negative in your math, right? Okay? Right. It's got to be a negative number. So I'm really hoping. Right? Once you get the components, which are these two, could you go on to figure out maybe from a vertical equation? Is it kind of like if you threw a ball straight up and then fall straight down the cliff? That would be an equivalent amount of time. So set up a vertical equation. You can get the time. And I'm giving you another big hint here. Guys, you're going to run into the quadratic equation. Okay, quadratic. So I gave you quadratic right here. Well, I should have said t instead of that. It's like at squared plus bt plus c equals 0, then t equals, and set up a quadratic. Okay? Right. But if you do it right, you should get exactly one of these times. If you do, you're doing it right. Okay? And then how far across? Can you guys say x equals v sub x times t? Okay? So take this v sub x times this t, and you should get how far it goes. Okay? These guys? All right. And then these scenarios are just the same. I just didn't give you guiding questions.
I want to go forward in time.
All right. Any questions? Are you guys ready for this lab tomorrow? All right. So tomorrow, be dressed for outside. Dressed for success.